I'm really excited to have the opportunity to tell you something I'm really passionate about, which is the technology of optical fibers, and in particular, as you will understand during the course of my talk, we are working here on a very special type of optical fibers that guide light in a hollow center or in an air core. I have the privilege of working at the Optoelectronic Research Center that you might not know, but is one of, if not the world leading center for research in optics in general, and more specifically in optical fibers. So, I would like to start my talk with something we are all very well familiar with. We are familiar with the object, the technology, but do you know what happens when we, say, take a picture and we want to store it in Pinterest, for example? Where does the data go? Or if we want to check what our friends are doing in Facebooks, where is this information stored? We might have heard that it is in the cloud, right? Is this the cloud we're talking about? Certainly not. It's not this the cloud. So what is the cloud? This is it. So it's corridor after corridor after corridor full of servers, memories, computers. The memories are still with magnetic tapes, magnetic disks in these servers. This is all our information, pictures, emails, secrets are stored. And so just to give you an idea, this is the Microsoft Azure data center in Dublin. They're still finishing it up. To give you an idea of the scale, look at the size of the track down there. This is several football pitches wide and several stories high, and it can contain up to 1 million servers. So where are these massive data centers located? Well, there's many around the world. These are those from Microsoft, but Amazon, Google, Facebook, they all have their own locations, okay? And all of these giant companies have very intelligent algorithms that try to guess what your interests are and put the data as close as possible to you, so that data needs to travel as little as possible. But sometimes you want some information that is stored somewhere in Japan or in Australia or in California. So how does data travel from your phone up to these data centers? It doesn't travel through the air the whole way. It certainly travels from the little antenna that is in the phone through the air for a little while. Okay, so the first few tens or maybe up to 100 meters, data travels through the air until you get to maybe your wireless hub if you are at home or in the office, or up to the 4G antenna. Then it might travel another 50-100 meters as an electrical signal, and after that typically it is transformed into an optical signal, into a stream of light. Okay? From that point on, which might be 50-100 meters from your house, it goes all the way to Sydney, following an optical path, okay? Following what we call as an optical network, and goes also through the oceans. So these optical fibers are laid down on the bottom of the oceans. And you know, I wanted to share a very nice video I found recently, which shows the evolution of optical cables, transatlantic or transoceanic optical cables through the years. Now you will see here, there's a date, 1989, so the pointer doesn't work on that. This video goes very fast, but it shows that in 1989 there was no optical cable anywhere underneath the oceans. Okay, this is 30 years ago. If you wanted to make a telephone call in the US, you typically had to rely on satellite. It was very, very noisy, very unreliable, very lot of latency, so it was not pleasant. And now I'm going to run the video. And you can see 1995, the first few ones, and boom, 2000, big boom. And this is what it looks like now. So we have hundreds of cables crisscrossing the Earth, tens across the Atlantic, so each of those is several thousand kilometers long. Okay? And this transfer information, huge amount of information, through optical fibers. This is what supports the internet. Okay, let me go a bit slower. So 1995, only a few cables there. 1997, first few transatlantic cable. 1998, first connection between the US and Japan. And then the big boom happened in 2000. Big telecom boom, if you remember, big boom, big bubble, and big burst. But this is when several cables were laid across the Atlantic, across the Pacific, and now this is where we are. So, how is this all possible? How can we transmit information through an optical fiber? Well, you need three main ingredients. You need a laser, which is a source of coherent light, very well focused and at a very precise color. This is what we need to encode information. Then we need a way to transmit information using this laser. You can think of as a Morse code, right? And now scientists use a lot more complicated algorithm, a lot more efficient, but the concept is very similar. You need a receiver at the other end, and you need a pipe, a way to transmit this flow of light and information. This is the optical fiber. So what is an optical fiber? This is the best image I could find. It's a very, very thin strand of ultra pure glass, the size of your hair. This glass is typically coated with a very thin layer of plastic, just to protect it, but this is what it is. And I just want to pass around a couple of these fibers so that you can touch for yourself. Just pass around. How is light guided along these fibers? Well, there's an excellent demonstration over there, so it's a lot better than my slide. But essentially, the key concept is that when a ray of light propagates through a transparent and dense medium, for example, water, and it hits the interface with a less dense medium, for example, air, like in this case, you have reflection, and this reflection is perfect, meaning that no light is lost in this interface. It's the best mirror that mankind has ever produced. Well, actually, it's nature has ever produced. Okay? So you can replicate this concept using a glass tube, for example, and you have the same concept. You have light can bounce multiple times, and at each bounce, no light is lost. And if you make this glass tube a lot thinner, slender, and longer, and you have the optical fiber, which I believe is one of the technological wonders of the last century. And I'm going to give you some data to try and convince you about this. So let me start with this question. Does anyone have an idea of how much fiber is there in the world at the moment? I've shown you there are hundreds of cables across the oceans, each of which is several thousand kilometers long. So you might say several thousand, several hundred, maybe 1 million kilometers. I mean, that is already a large number, right? Maybe 10 million? 4 billion, over 4 billion kilometers of fiber installed right now in the world. Just to give you an idea of how much it is, if we were to put it one strand next to each other, we need to look at astronomical distances. Okay, so if we were to attach it to a satellite, to a spacecraft, we would travel way beyond Saturn, Uranus, and almost get to Neptune. This is how much fiber we have produced. Okay. Last year alone, we produced over 300 million kilometers of optical fiber. How much is that? Well, it's about 9,000 times the circumference of the Earth. It's about to the Sun and back. This is what the astronomers call 2 astronomic units. And if this fiber were produced in just one location, which is not the case, but imagine if in order to produce this amount of fiber, we will need to fabricate it at a speed of 11,000 meters per second. This is 32 times the speed of sound. The fastest jet that we've ever managed to produce only goes at 6 times the speed of sound. Okay? Not only this, but these fibers are made of material that is incredibly pure and transparent. So, if you were to launch some light in one end of the fiber, imagine this laser pointer here. Okay? You launch it to one end. After 100 kilometers, so you put some fiber from here up to London. You have a friend in London. You shine this laser pointer here. After 100 kilometers, you still have 1% of the power. This is incredible transparency. If you take one of these glass windows, they look transparent, but the thickness is a few millimeters. If you were to look vertically down the glass window, already after a meter, you will see that there is very little transmission. Okay, so this is incredibly pure and transparent medium. Despite this fiber costs about £6 per kilometer. This is a lot less than a nylon fishing line. So it's really amazing mass scaling of production. And perhaps the most astonishing number is the amount of information that they can carry. So the little strand of, like your hair that you might have seen, can carry, information is typically measured in bits per second. Bit is either 1 or a 0. This is how we send our information around. Okay? So in 1 second, blink of an eye, your fiber can carry this many bits of information. This is 100,000 billion bits of information. So how much is it? Well, you can have simultaneously 3 billion Skype calls. For example, one half of the world talking to the other half of the world. And everything, all the traffic flowing through the fiber that you've seen in the past. Or 30 million Netflix moving simultaneous downstream. So every single household in the UK download movies all through one of these tiny strands of glass. So it is really astonishing. So you might wonder, what is there else to do? Why am I working on optical fibers? This graph here shows the average data traffic flowing through 2 international cities, say between London and Paris. And it shows how through the years it has increased. Okay? Over the last maybe 30 years, traffic has on average increased about 30% every year. We keep finding applications and new ways of sending more and more data to the network. So this is the astonishing number of bits that a single fiber can carry. Okay, so in 2014, we could have sent the whole information between London and Paris through one single fiber. It's actually a pair, one per direction. Okay? So now we cannot do it anymore. You might think, okay, what's the big deal? We put a few fibers in parallel. They're very thin and small. It's not a big problem, right? But this traffic is going to continue growing for 30% a year. So at some point we might need 4, 10, 30, 100. At some point it will become unsustainable. Okay? So this is why we need radically new technology, because we need more information. This is probably the most difficult graph in my whole presentation. So let me explain it a bit, some detail. So this shows on the vertical axis you have the loss of an optical fiber. Okay? If you look here, I'll explain better. So this is what fraction of light remains after it has propagated through a 1 kilometer. So up here, you have 10% of light remaining. Down here, you have 96%. Almost all of the light is still there after 1 kilometer. So clearly, this is where we want to operate. Okay? In the horizontal axis, we have wavelength. Wavelength, as you know, light is a wave, is an electromagnetic wave. And every wave can be characterized by this parameter called wavelength, which is the distance between two adjacent peaks. Okay? So this is depending on the size of the wavelength. Electromagnetic waves can become like radio waves. These are wavelengths very long, meter or tens of meters. And on the other extreme, you have something like gamma rays, where the wavelength is 1 billionth of a billionth of a meter, extremely small. Okay? Somewhere in between, the small part of your electromagnetic spectrum, we have this graph here. And in the even smaller part is where our fibers are incredibly good and transparent. Okay. So this is where we want to operate. And in order to operate there, we have a limited bandwidth. Bandwidth is proportional to the amount of information that we can transmit to the fiber. So my research is, to put this very simply, to try to develop radically new optical fibers with lower loss and wider bandwidth, so more capacity for more information. It's not so simple though, because this technology has been optimized for the past 50 years. And it has now reached fundamental physical limits. So there's no way with this current technology we can improve. This is it. Scientists have for many years looked for other glasses, other ways to transmit light with better properties, but so far nothing is on the horizon. And no other light-guided medium exists that gets even closer to the performance of these fibers and this glass that I've shown. So where else can we look for an alternative? Look up. Space. Vacuum is the best possible light transmitting medium. If you think about it, stars transmit the light, light comes from these stars and propagates through millions of years. Because there is no scattering, no absorption, no attenuation. It's the best possible medium. But even the Earth atmosphere, despite the fact that we have oxygen, nitrogen molecules, is still a very good medium to transmit light. The distance between the sun there and the camera that took this picture is several thousand kilometers, and as you can see, light is transmitted very well. Right? So, atmosphere is very transparent. It's good, but we need to find a way to guide light, because light tends to transmit in straight lines, and straight lines are not very convenient. You may want to make a bend around a bend in order, for example, to bring it inside your house, for example. So what we are looking for is a way to waveguide light in an air hole. There's a number of problems with this. Well, as I said, light like to propagate straight. How can we make it bend? And also another point that is shown extremely well in the demonstration over there, you might take a look later on, is that light likes to propagate in dense media, like water or like glass. It doesn't like to stay in less dense media like air. So how can we convince it to stay inside the core of an optical fiber? This is a problem that has fascinated scientists since the end of the 19th century. And the solution is to surround the central hollow region with a microstructural region of some sort that plays the trick of convincing light or forcing light to stay in the center. And the trick is something that we have borrowed from nature. So my colleague Martin, at the end of this evening, will tell you a lot more about it. But this butterfly is an example of such a natural trick. In the wings, we have periodic scales of the right size to reflect just this color of light. This is an optical trick this butterfly used for their purposes. We have borrowed it in order to make these hollow fibers. As you can see, there's a wide variety. They are all roughly the size of your hair. They all have a hollow core in the center and a range of very thin glass membranes. So the size of these membranes can be 1 millionth of a meter, essentially, or smaller. So it's quite an engineering beauty, the fact that we can make fibers with such a small, delicate features over several kilometers long. Okay, and I have a few samples here for you to look at during the break, if you're curious. And to prove you that they work a bit like a butterfly wings, this is what happens when you put them under a microscope. You see these beautiful colors developing, and there are indications that some of the colors of light are captured, and only a fraction of those are let through the fiber. This is a phenomenon that we use to force light to stay in the center. So what exactly do we do here in Southampton, researching on these fibers? Well, we do a lot of modeling to try and understand the physics and to try and engineer the best possible structure that guides light with the best possible properties. And we study not only the electromagnetic propagation, but we also study ways to fabricate these fibers. So we have models of the fluid dynamics process of the fabrication of such fibers. And this is shown on the image on the right. This is a simulation of what happens when we draw a fiber. We inflate, we put positive pressure in order to achieve membranes which are as thin as possible. We not only simulate fibers, but we have the luxury of having one of the best, probably the best, fiber fabrication facility in the world. And so we also fabricate these fibers. Okay? Here you can see on the top one optical preform. I have an example here if you are interested later on. This is a glass preform. It is lower down. You can see there a furnace at about 2000 degrees C where this glass melts, and at the bottom of the furnace the optical fiber is fabricated. And here in this image you can see a preform being lowered down into the furnace. The color here is just the heat coming out of the furnace. And this process works wonderfully. So these are two examples of world record fibers that we produced last year. Again, these membranes are about 1 millionth of a meter. And this image to me is quite astonishing because we managed to capture not only the structure of the fiber, but also light being guided in it. So we launch light from the other end. And you can see it in this hexagonal shape in the center. And I think the truly astonishing thing is that you can see the light is not touching the glass. Okay? So it's guided in air or in vacuum if you want, without touching the glass. And you can really bend the fiber tightly around your finger and light keeps following the path of the fiber. So where are we with our research? I'm just showing this summary slide that shows the evolution of the technology as we've improved our understanding of the physics, our ability to fabricate fibers. In the graph here I'm showing the loss. Again, it's the same parameter I showed you before. So high means bad. And you can see how over the years loss is reduced very, very considerably, to the point where now we can fabricate fibers which are very close to the loss of conventional glass fibers. They have a much wider bandwidth, And our models indicate they have the potential to significantly outperform conventional fibers. So this could be the revolution in optical fiber technology of the future. It is something that was invented here in South Africa. I don't have time to go through other applications. I've decided to focus just on data transmission, but this is not the only application these fibers are good for, or useful for. So I would be very happy to talk you through more about this in the question and answer session or at the end if you want. But for example, we are working in laser delivery. We are working in nonlinear imaging, for example, for the detection of cancerogenic tissues, sensors to make autonomous vehicles able to navigate without the GPS, and many other applications, again, this pretty outstanding technology. And with this image of a fly holding what could be a revolution in optical fiber technology, I'd like to thank you a lot for your attention. I'm very happy to take your questions. This is an image of the team at the University of Southampton, our core optical fiber group. We have, as Andrei mentioned, we have founded a spin-off that currently employs about 30 people in the local area and is growing very fast to develop this technology. We are all very excited about it. Thank you very much for your attention.
So thank you again, Francesco, for that great talk. So we have a bit of time now, a couple of minutes for time for question and answers. Just before we do, I'd like to say, no such thing as a stupid question. So if you've got anything in mind, anything wasn't clear, or an idea that Francesco might want to bring into his company, make him a lot of money, feel free. Alternatively, we've got our speakers are going to be around, hanging around, having a few drinks. We're paying the bar tab, so can you make sure you get your money's worth from them by asking them questions. Okay, so if you want to, if anyone's got any questions, stick your hand up and bring over a mic to you. Yeah?
How long are you able to make the fibres, given the demand is for millions of kilometres a year? Are you just making them a kind of a few inch length, or can you make them on scale, as it were?
That's a very good question. We are a research organization. We are not geared up for volume production. So the scale of fiber production we can support is about several kilometers, tens of kilometers. In the local startup, we're aiming to make thousands of kilometers, not millions of kilometers. But for that, you need massive investment and plants that are massive. So in China, they have a fiber plant with 30 drawing towers, each of which is 35 meters tall. Okay, it's all automated, all controlled by robots, and this produces several millions of kilometers, or maybe 100 millions of kilometers per year. It's a different scale. We are not doing that.
How do you interface between hollow core optical fibers and regular ones?
It's a good question. Typically, fibers are connected together by applying a lot of heat and fusing the glass. So when you have glass and glass fiber, you put them close together, you apply a lot of heat, the glass fuses, and you're left with something that is almost, you won't be able to detect that there was a break. When you connect hollow core fibers, you need to be more careful because they have very thin and delicate structure in the center, so you need to be careful with the heat you provide. If you provide too much heat, you will collapse the whole microstructure. But it is possible to apply heat only on a radial annular ring around the fiber. And it is possible to fuse them together and produce a strong and robust junction with no optical loss. It is possible.
You said that the light in the hollow core fibre doesn't actually touch the sides, so how does it get deflected?
Good question, you got me there. So, that image shows light on a linear scale. Okay. So, this is a kind of a bell-shaped intensity profile of light, kind of here. There are tails. The tails, very, very low down, will touch the glass. So there is some interaction. However, it is very, very little. So over 99.99% of the light is guided there. So it's a very tiny fraction of light that is guided into glass. And because of that, we can guide light even where the glass is opaque. Even where the glass would not transmit, you can still transmit inside the core.
Great, if that's all our questions, I think we're running out of time.
Just a short one.
I'll really branch it.
If the current cables go under the sea for 1,000 square meters, you say after 100 it is 1% only. There are some repeaters, or just little is left?
Excellent question. Yes, absolutely. So every about 100 kilometers, the power is too low. So you need to boost it up. So we have optical repeaters to do this. So the signal never keeps remaining in the optical domain. It's still an optical signal, and there is something that was invented by the director of my center here in Southampton that is really enabled this, the internet really, and is the optical amplifier. It's something to boost up the signal. So roughly about every 100 kilometers under the sea, you have one of these optical amplifiers. They're big sausages, like 40 centimeters wide, a few meters long. They contain all the electronics. Obviously, they need to be powered, so there's an electric cable beside the optical cable, and you have a few hundreds of those laying on the ocean floor.
Great. So I'd like to thank Francesco again for giving a quick round of applause.